which can be either configured as a positive edge triggered or negative edge triggered, depending on the clock pulse which we offer for our flip flop. And every D flip flop is having the capability to store and propagate either logic 1 or 0 according to the input. It is attached with the multiplexer, and as we all know, it is considered to be a 2:1 multiplexer. So obviously, two inputs here is considered to be, one is scan in. SI stands for scan in data, and here D is the normal input which we deliver. So at one instant of time, either SI, meaning scan in, will be carry forwarded at its output Q, it will be carry forwarded at its output Q, or the D will be propagated to output Q. So what happens is, for the initial flip flop, either scan in will be propagated. So the output is fed over here. Likewise, the output is fed over here. So the output of each and every flip flop is fed as an input for the next multiplexer. So in this fashion, my scanning will take place either by taking an SI data for the overall module, or in other words, based on the control input, my D will be propagated. So this kind of scan-based approach is possible. But the greatest disadvantage in this design is that for loading either the scan-in data or the D for the first four D flip-flop, we are in need of 8 clock pulses. So 8 clock pulses are mandatory for loading the data, either SI or D. And likewise, the same 8 clock pulses has to be offered for deloading the data. So it is going to be time consuming, so which can be easily overcome by parallel scan-based testing. Here, parallel scan-based testing is the one wherein each and every register is associated with its own write control signal, data write, row axis and column axis. So this module will let you know, for simple case, we have just mentioned only a single D flip-flop, but multiple D flip-flops can be incorporated inside my system, which have a provision of individual row axis and column axis. So simultaneously, all the registers are able to get the address and get the control signal for writing the data onto it or reading the data. So in this way, time consumption is greatly reduced in parallel scanning. So you can just draw the diagram and state the advantages and disadvantages as far as this particular topic is concerned. Thank you for listening.
So good morning all. In continuation with the previous session, ground wave propagation, now we have a discussion on the reflection by the ground. Will see the effect of the reflection that is made by the ground for the propagation. So as we know, in case of ground wave propagation, our wave is going to reach the receiver either in a direct way, if both the antennas are in line of sight communication. So that wave may directly reach the destination, or it may reach the destination through reflection by the ground. Why? Because we know that in ground wave propagation, my wave is going to glide over. That is, it is going to travel along the surface of the ground. So there might be chances of getting reflection by the ground surface. So we need to see how much reflection is going to take place for a electromagnetic wave, that we are going to see it today. It is a continuation from the ground wave propagation. Now we are going to see the effect of ground reflection by the expression derivation of reflection. That is the plane earth reflection. Plane earth reflection. In this we are going to plane earth reflection. Here we are going to see the relation of how the signal is getting reflected by the ground surface and how it is having impact on the wave propagation along the ground surface. First let us consider a transmission system where the antenna, transmitting and receiving antennas are placed above the ground surface. It is the earth surface. Here, the transmitting antenna is placed over here at the height of HT. Similarly, consider there is a receiving antenna at the other end of the earth surface, which is elevated at the height of HR. Okay, from the transmitter to receiver, the wave either it may reach in a direct way if it is a line of sight communication because they can face each other. So it is a direct way. Okay, so otherwise the signal may reach the destination, that is the receiver, through reflected wave. So the wave may reach in a direct way or it may be travel through to the receiver through reflected wave. So consider, so this is the angle which is making to the plane angle psi 1 and this one is phi 2, sorry, this one is phi 2 and this one is phi 1, and consider the angle with the incident angle that is making to the ground surface to the vertical line, that is the normal line as theta. Here theta is the incident angle to the normal line to the ground surface. So by considering this diagram, we are going to derive the expression for the reflection that is made by the ground surface to the reflected signal. Okay, from this diagram, we can conclude the total field that is received by the receiving antenna can be written as received energy is the combination of both direct wave and reflected wave. So the total energy that is received at the receiving antenna will be direct wave energy plus reflected wave energy. So, next we have to consider the practical conditions of ground reflection surface. Since we assume that our earth is a flat and smooth surface, it is an assumption, but practically it is not a smooth surface. It will have irregularities over the earth surface. So we have to consider the actual practical conditions of our earth surface. If we consider our earth is a smooth finite conductor, if this be the case, okay, my signal will get reflected by the ground surface, but it will differ from the direct wave because in direct wave your signal will reach the receiver through line of sight communication, so that no changes will be experienced by the direct wave. But if your signal is getting reflected by a ground surface, that signal will be altered in magnitude as well phase, since your electromagnetic wave is getting reflected by the ground surface, its magnitude and phase of the signal is altered. Okay, so at the receiver side, when you receive direct wave and the reflected wave, both will differ in amplitude as well as in phase. If this is for the condition of assuming our earth is a smooth flat surface. So but practically my earth is not a smooth conductor, it is having irregularities as we know. So this irregularities, if it is severe irregularity between the transmitting and receiving antenna, your signal is getting scattered because my earth is a rough surface. It is having so much of irregularity. When the signal is incident on the irregularity, it is getting scattered in all the directions, so that the final resultant signal reaching the receiver will be very low in amplitude and as compared to the direct wave. Okay, so that is due to the reflection. That is actually here the reflection becomes scattering when the surface is not a smooth one, irregular and rough surface. Okay, So that here the crucial factor that is going to impact on ground wave propagation is the reflection that is made by the ground. Whether it is going to have a smooth reflection or a rough reflection. If it is a rough reflection, it will be a scattered signal. The resultant signal will be very very low compared to the direct wave. So that is a point that we should remember here. And then now we need to consider the roughness factor. How much it is getting deviated from the flat surface. So instead of having a flat surface, practical cases where we have irregularities, how much it is getting deviated. Okay, that particular variation will be defined by the parameter called roughness of the earth. Roughness, it will tell you how much it is getting irregular in the surface of earth. So roughness R is represented by R equal to 4 pi sigma into sin theta divided by lambda. So this is the factor which is going to tell you the roughness level of your earth surface between the transmitting and receiving antenna. So this variation will be defined by the parameter R, that is the roughness, where sigma is representing the conductivity of the earth surface and theta is the incident angle to the ground surface, incident angle, and lambda is the operating wavelength, that is the electromagnetic wave which is traveling between the antennas having a specific wavelength. So this is a factor as I told you. By calculating the value for the roughness, so typically if the value of the roughness is less than 0.1, that will tell you that the reflecting surface is a smooth one. If the roughness value is above greater than 10, then it is a rough surface where scattering will take place. This is a conclusion that we can get from the expression, and the typical value is given here. But the practical case, we have considered our earth is a flat surface which is assumed as a smooth surface, but practically, as I told you, it is not a smooth surface. It is having irregularity over the entire distance between the antennas. Again, another issue is my earth is not a earth is usually assumed as a dielectric and conductor also. Usually it is assumed as a conductor as well dielectric, but practically it is not a perfect conductor, not a perfect conductor, and not a perfect dielectric too. We have considered this particular representation. Why? Because if it is not a perfect dielectric, it will have a dielectric loss. Similarly, if it is not a perfect conductor, it will cause some signal loss while propagation that is taking place between the antenna. Okay, so since this is the practical case, we are going to experience some amount of signal loss due to not a perfectness of your conductivity and dielectric property of the earth surface. So for this in order to understand it clearly, we need to derive some mathematical expression which is going to tell us how much of the surface roughness is going to affect the wave propagation. The reflection is going to contribute part of the signal reception at the receiver. So we need to analyze the reflection that is made by the ground. So in order to do the analysis, we are going to do some mathematical expression analysis for roughness. Consider Maxwell's equation for medium. Since we have considered earth reflection here, the earth is not going to have a perfect dielectricness and perfect conductivity. So for this condition, that is for a medium, since here my earth is a medium, that medium is going to have conductivity sigma and permittivity epsilon. For this kind of medium, my Maxwell's equation is giving the relationship, that is del cross H equal to J, current density is J plus dou d by dou t. So this is the Maxwell's equation for the medium which is having electric conductivity and dielectricity of the medium. So conductivity, this electric current density, I can write it as sigma E. Sigma is the conductivity of the medium, and then this can be written as epsilon into dou E by dou T. So this particular expression, it is actually the equation 2 is derived from equation 1 by the condition of assuming my wave is getting propagating in a sinusoidal manner. When you consider time varying behavior, you can write it like this, because your electric field is going to vary with respect to time. Because of that, I have just replaced this term by means of this, because my wave is getting traveling in a sinusoidal manner which is varying with respect to time. So I have derived this, and then so when you consider the conductivity over the Earth's surface, this permittivity now depends on the permittivity, that is the dielectric property of your Earth. So to represent that, I am here representing this epsilon dash as uh, a new parameter which is associated with the permittivity of your Earth medium. So that this epsilon can be written as, sorry, epsilon dash can be written as epsilon plus sigma by j omega. This particular permittivity parameter is meant for the ground reflected surface. So as you can see, this depends on the permittivity of the medium plus the conductivity. Since my Earth is the combination of dielectric and conductivity, so it is contributing both conductivity sigma and permittivity epsilon, which is the complex quantity. As I can see, it is having a real part and imaginary part. So my epsilon dash is a complex quantity. So now we have come to know that my Earth is going to provide some conductivity plus some dielectric property. So I'll just get the relation for the conductivity and the permittivity. Now we are going to derive the reflection coefficient for different waves, because my signal is getting uh, generated at the transmitting antenna, it is getting reflected by the ground surface and it is reaching the receiving antenna. For this case, your signal either may have a horizontal polarized signal or it may be a vertically polarized signal. Polarization, as you know, as you can recollect from the previous unit, that the polarization is the electric field orientation between the wave propagation. When you have the electric field strength along the vertical direction, it is a vertical polarization, and if it is horizontal nature, it will be a horizontal polarization. For both the cases of polarization, we are going to have the reflection coefficient. The reflection coefficients for horizontal and vertical polarizations are given by RH equal to square root of epsilon 1 cos theta minus square root of epsilon 2 minus epsilon 1 sin square theta divided by epsilon 1 cos theta plus epsilon 2 minus epsilon 1 sin square theta. This is for horizontal polarized signals reflectivity, and the another expression for vertical polarized signal is um, epsilon 2 minus epsilon 1 into cos theta minus square root of epsilon 2 minus, sorry, epsilon 2 divided by epsilon 1 minus sin square theta divided by epsilon 2 by epsilon 1 into cos theta plus square root of epsilon 2 by epsilon 1 into minus sin square theta. So this is the expression for reflectivity of your vertically polarized signal. So for this two expression, we need to substitute the permittivity condition, since epsilon 1 is meant for the transmitting antenna side dielectric constant, and epsilon 2 is for ground reflected signal. Epsilon 1 is the direct wave permittivity and epsilon 2 is the reflected wave dielectric permittivity. Okay, we need to consider the conditions here. As you can see, your wave is, your both transmitting and receiving antennas are elevated from the ground. It is placed over the air medium. So the signal that is getting emitted by the transmitting antenna is emitted in a medium called free space. So that the free space permittivity will be epsilon naught. Okay. So first we'll consider the uh, horizontal polarized reflectivity. So before writing that expression, we will substitute, we will consider the permittivity medium. As I told you, the signal is getting originated from the free space, so epsilon 1 can be replaced by epsilon naught, which is the free space permittivity. Since my antenna is transmitting the wave in a free space, so this can be replaced by epsilon naught. Similarly, uh, medium 2, when your wave is getting reflected by the ground, okay, here earth permittivity should be considered, so that epsilon 2 is, I can write it as epsilon dash, that is equal to epsilon plus sigma by j omega. This we are deriving from the expression from here, epsilon dash. Okay, and then we know from the diagram, so this is the angle psi 2, so which is where we know that theta is the incident angle to the ground. So this phi 2 and theta can be interrelated by, so theta can be written as 90 minus psi 2, or psi 2 can be written as 90 minus theta. Okay, so when you consider this, sin psi can be written as sin 90 minus, when you substitute this, so you can substitute 90 minus theta, this can be written as cos theta. Similarly, if you want uh, cos psi, cos 90 minus theta, you can write it as sin theta. So by assuming these conditions, we substitute all these things in equation number 3. So to get reflected, that is the horizontal reflection coefficient, which can be written as square epsilon 1 should be replaced by epsilon naught. Square root of epsilon naught cos theta. Cos theta can be replaced by sin psi. So directly I will do that. So sin psi minus square root of epsilon 2. Consider epsilon 2. Epsilon 2 is should be replaced by epsilon plus sigma by j omega epsilon. This is contributed by the ground reflection. That's dielectric constant. So epsilon plus sigma by j omega minus, and then my epsilon 1 is epsilon naught into sin square theta. Sin theta can be written as cos phi. Okay, so that this can be written as cos square psi. That's it. Okay, this is the numerator part. Similarly, for denominator part, epsilon naught sin psi only changes the sign that is existing between the two terms. So square root of epsilon by j omega minus epsilon naught cos square psi. This is the expression phi. Okay. So when you take this square root of epsilon naught into the term, we can write so RH equal to sin psi minus square root of epsilon. Epsilon, when this get into the square root term, this will become epsilon by epsilon naught plus sigma by j omega epsilon naught. Okay, this one minus epsilon naught, and when it comes here, it will cancel out. So cos square psi. Similarly, sin psi minus square root of plus sigma by j omega epsilon minus cos square psi. So this is the expression number 6. Okay, I'll repeat the substitution procedure here. We have considered the horizontal reflection coefficient and vertical reflection coefficient. Since the first medium is free space and the second medium where your wave is getting reflected by the ground, so it is considering the permittivity and conductivity of your ground medium, so that it gets the expression epsilon plus sigma by j omega. So and then the incident angle is related with the plane angle phi 2 and theta, so that this can be written as theta is 90 minus xi2 or xi2 equal to 90 minus theta. So when you substitute this in the horizontal reflection coefficient, so epsilon 1 is replaced by epsilon naught and epsilon 2 is replaced by epsilon plus sigma by j omega, and then theta is here replaced by phi. Sin theta means it is a cos phi. If it is a cos phi, it is a sin theta. Okay, so I have just substituted here. I have taken the square root of epsilon naught term inside the second term. When you take that, finally you will get the expression like this. So we will continue with the last expression. Okay, for simplification, we will consider epsilon by epsilon naught as epsilon r. This we know that the permittivity of the medium equal to relative permittivity multiplied by free space permittivity, so that you will get the total permittivity of the medium. So epsilon by epsilon naught equal to epsilon naught. Similarly, for my simplification purpose, I am going to take sigma by j omega epsilon naught as x. Okay, so these two substitution I am going to make it for the final expression. So the reflection coefficient, horizontal reflection coefficient RH equal to, when you write the expression for this, sin psi minus square root of first term will become epsilon r minus this entire term. Now I can write it like x. So x, sorry, here you can write it so you can take sigma by omega epsilon naught as x. So when you write like that, it will become, yes, it will become epsilon r minus jx into minus cos square psi divided by sin psi minus square root of epsilon r minus jx minus cos square psi. So this is the final expression which is related with the relative permittivity of the medium and the angle which is making, that is your incident wave that is making to the plane air, that is what psi. So initially it was related with the incident angle, now it is related with the plane angle which is the ground surface angle, that is psi. So similarly, by doing the same substitutions what you have done for the horizontal polarization, we can write the expression for vertical polarized signal reflectivity, RV equal to epsilon r minus jx into sin psi minus square root of epsilon r minus jx minus cos square psi divided by epsilon r minus jx into sin psi plus square root of epsilon r minus jx minus cos square psi. So this is the expression for vertically polarized signals reflectivity. So we have written the final expression which is relating your relative permittivity of the medium with the plane angle of the ground reflected signal. So when you do that, finally we are achieving the horizontal signals reflectivity and vertical signals reflectivity. So as you can see from the final expression, it is consisting of both real terms and imaginary terms. Okay, so the these two expressions can be finalized, uh, can be easily represented by real part of horizontal polarized wave with magnitude, and vertically polarized signal is a combination of real part of vertically polarized signal and phase of, which is a complex quantity consisting of both amplitude and phase, since the final expression is containing imaginary terms and real terms as well. So Simply we can write the final expressions as real part and imaginary parts of the reflectivities of both horizontal and vertically polarized signals. So we'll conclude by summarizing what we have seen today. We have considered the plane with reflection. Since we are dealing with the ground wave propagation, your signal is going to glide over the Earth's surface. So when it is traveling along the surface of the Earth, it gets reflected by the ground surface. Because of that reflection, as we know, the signal may reach the receiving antenna either in a direct way or getting reflected by the ground surface. So when it is going as a direct way, so there is no issue at all because it is going to reach as it is. But when it is getting reflected by the ground surface, here your wave is getting interacted with the ground. But ground is not a perfect conductor, as we know. Similarly, it is not also a perfect dielectric, so it is going to contribute some amount of loss. So when the signal is getting reflected by any surface, the magnitude and phase of the signal will get altered. Okay, so the receiver, the total received signal will be direct signal and reflected one. By considering the practical scenarios of our Earth surface, we have to do some modification in the general expression. We have considered Maxwell's equation for the reflection impact on the electromagnetic wave propagation. We have considered Maxwell's equation, which is having dielectricity plus conductivity, both parameters. So we have considered del cross H equal to J plus dou D by dou T. So from that expression we have taken the relationship of electric field intensity. D is epsilon E because the permittivity here is a matter. So electric field intensity D is replaced by epsilon into E. So we have started with that. We have considered two cases. One is free space permittivity. When it is interacting with the earth, there will be a medium permittivity, that is epsilon. Okay, we have considered two cases. We have considered the reflection coefficients of both horizontally polarized signal and vertically polarized signal. Finally, the cases we have considered here, free space permittivity is replaced by epsilon naught, and our medium permittivity epsilon 2 is replaced by earth permittivity and conductivity. This is a complex quantity, and we have related the incident angle with plane angle psi. So when you do that, finally we can derive the. We have to substitute all the assumptions here, and we have to substitute in the reflection coefficient expression. Finally, we have derived and we have summarized with the reflection coefficients for both horizontal polarization and vertical polarization. Thank you.
Good morning. Today we will start with